Today we're going to talk about sets. We're not going to dive into this too deeply, but we'll need to study sets to study probability later on. All a set is a collection of distinct, well-defined objects. Distinct here means that sets cannot have more than one of the same element, while well-defined means that objects in the set must be concrete things. For example, we could write down a random of collection numbers, like so. Or we could write down a set consisting of the weekdays. Or we could do something like write down a set of simple shapes. Now we might want to talk about whether an object is in a set or not. And to do this, we use this weird E-looking thing, which we read as in. So for example, Tuesday is in the set of all weekdays. Okay, another important idea that we'll need is the concept of a subset. So we say that T is a subset of S if every element of T is also an element of S. Looking at our collection of shapes, square and X are a subset because every element on the left also shows up in the set on the right. So with the basics of sets under our belts, let's see a better way of building sets. Most of the sets that we'll talk about are either infinite or just have way too many elements in order to be able to write them down explicitly. So we need a better way of defining such things, and that's where set builder notation comes in. If we're working in a set S, set builder notation has us define a set by specifying the properties its elements must satisfy. So as an example, let's take the set of all countries. And let's define the set M to be those countries that have over 100 million people in them. Now, as of this video, there are 15 such countries, but I don't want to take all the time to write them down. But nonetheless, we know that each of those countries is going to show up in M precisely because that's a property that I force them to satisfy. If we take an element from M, we can rest assured that it satisfies this property. But on the other hand, if we're given an arbitrary element and we want to check that it's in M, we need only check if it satisfies the given condition. So for example, we might want to check if Japan is in M. And if we did so, we would look at the population of Japan, see that it's over 100 million, and be like, yep, it's in M. Now, working in mathematics, we'll probably be using numbers a fair amount, so here are some sets with which you should be familiar. The naturals, which are just the positive whole numbers. The integers, which add in the negative numbers and 0 to the naturals. The rationals, which are effectively the collection of whole number fractions, and notice the use of set builder notation here. And finally, the reals, which we can't write in set builder notation for complicated mathematical reasons. Okay, so what can we do with sets? How can we combine them to make new sets? To set up our definitions, let's let E and F be subsets of S. The union of E and F is the collection of elements which are either in E or in F. So as an example, let's take E to be the set of even numbers, and let's take F to be the set of, say, prime numbers. The union of E and F are those numbers which are either even or prime. Right, and to illustrate this, we can write a few of them out here. Okay, so next up is the intersection. The intersection of E and F is the collection of elements which are in both E and F. And if we use the same example sets above, then the intersection of E and F is the collection of all numbers which are both even and prime, and there's only one such number, namely the number 2. Next is the complement of a set. If we take the complement of E, we're asking for all those elements which are not in E. So again, if we keep E as the set of even numbers, then the complement of E is the set of all numbers which are not even, namely the set of odd numbers. Now our last operation isn't like the previous three. It's quite different, but it's important all the same. The Cartesian product of E and F is the collection of all pairs E, F such that E is in E and F is in F. Keeping E as the evens and F as the primes, we're going to see that 2, 7, and 1031 are both elements of E cross F, and this is because the first number in both is even, while the second number in both is prime. On the other hand, 4, 9, and 7, 5 are not in E cross F. In the first case, the number 9 is not prime, and in the second case, the number 7 is not even.